Hello, everybody. Welcome to TWSS 2021 for our second talk of the day. Thank you so much for joining us. Today's presentation is going to be given by Luke Adams. Luke is a graduate student at the University of Colorado, Boulder. He's actually working with Dr. Cary to improve kinetic plasma simulation algorithms. And on that note, I will let you go ahead and take over, Luke.
All right, so hopefully you can hear me.
We can, you sound good.
Perfect. So yeah, today I'm going to be telling you about some work we've done to understand how grid instabilities arise in electrostatic PIC algorithms and how we can mitigate those. So in PIC simulations, we can develop a non-physical instability when we don't resolve a plasma well enough. So in this plot here, I'm showing the results of a simulation, one-dimensional electrostatic PIC simulation with periodic boundary conditions. And we propagate an electron beam through the simulation with a neutralizing background density. Now, physically, that should be a totally stable system. However, in the simulation, as you can see along the top here in these four phase space plots, we develop an oscillation that eventually breaks into thermal noise. And you can see that here in the energy plot below as well. The thermal energy in blue increases over the simulation, and that causes the total energy of the simulation to increase. And so this is obviously a problem if we want to have high fidelity simulations. Now, the conventional wisdom on how to resolve this is that we need to choose a grid size so that it resolves the Debye length of the plasma. The Debye length is this characteristic scale of a plasma on which it screens out electric charge. And you can see it's related to the temperature. And so what will happen is if we set up a simulation with a plasma where the Debye length isn't resolved, it will just heat until the Debye length is resolved. Unfortunately, resolving the Debye length makes simulations a lot more demanding if the physics we want to resolve is on a much larger scale than the Debye length. So ideally, we'd like to not have to resolve the Debye length. And then additionally, if we have to use these really small these small grid cells, then we also have to use small time steps for stability. And so it makes it really expensive to run these simulations. So the presenter you're going to hear from next, Catherine Wolfinger, actually has run into these issues in simulating plasma channel expansion. So today I'd like to talk about some ways that we can avoid these grid instabilities. I'm going to start with a review of electrostatic PIC, and we'll talk about the momentum conserving PIC algorithm that VSim will generate by default if you ask it to give you an electrostatic PIC algorithm. Then I'll tell you about a different energy conserving PIC algorithm that we can actually implement into VSim. And to kind of spoil the end of this story, I think you should strongly consider using this energy conserving PIC algorithm if you're concerned about grid heating in your simulations. We'll talk about instability growth rates for both of these algorithms. And then I want to switch gears and tell you about some work we've done to create a new PIC algorithm that we hope can address these to an even greater degree. In order to do that, we'll have to do a few slides of math, starting with the Low Lagrangian and then deriving a related method called particle and Fourier. Then we'll approximate that using cubic splines, and then take a look at the growth rates and convergence properties of this PICS method. So as you probably are aware, in a PIC algorithm, we have continuous particles that are evolving in a simulation domain that's been discretized by a grid. And on that grid, we have field quantities like the charge density and electric field. And in order to advance the simulation, we first scatter the particle charge to nearby grid cells. Then we solve for the fields on the grid before interpolating back to the particle locations, interpolating the forces back to the particle locations, and then we can use that force to advance the particles in time. Now I want you to notice that both the scatter step and this gather step require an interpolation that goes between these continuous particle quantities and the discrete grid quantities. Traditionally, or most commonly, an area weighting interpolation is used. And so I have a kind of schematic representation of how an area weighting interpolation works. We have 4 nodes here represented by the circles. And then imagine we have some charged particle sitting here at this intersection. Then each node gets the amount of charge that is proportional to the area of the square or the rectangle that is opposite it. So this orange node here gets only a little bit of charge. The blue node gets a lot of charge. And there's an obvious generalization of this to 1 dimension and 3 dimensions as well. This is what VSim will generate by default when you ask it to create a PIC algorithm for you. But this isn't the only interpolation we can use. And in fact, area weighting is just one of a family of interpolations called B-splines. So here in this lower plot, I have a plot of the 0th through 3rd order B-spline. 0th order here is also known as nearest grid point interpolation, where you just pick the closest grid point and put all the charge onto that. 1st order here in red is also known as a tent function, or again, this is just area weighting by another name. But there's this whole family of higher order methods that we can use. And you can see the 2nd and 3rd order here. What makes these B-spline shapes different is that they have more continuous derivatives and they deposit charge to a wider area. So more grid cells are going to get charge from a single particle. That does present a few downsides though. These wider stencils are slower because each particle has to interact with more different cells. And it also makes it more difficult to think about boundary conditions because now particles can have an extent that it goes beyond a single cell. So with that in mind, let's talk about how the standard momentum conserving algorithm works. So if you ask VSim to generate a PIC simulation for you, it will create a scatter step that looks like this. So for each particle, we compute the amount of charge that should go on each cell using this interpolation function S. And I've used S here to kind of indicate that we can think about these interpolations as a shape that the particle actually has in physical space. And then the amount of charge we choose to put on each node is just the amount of the shape of this particle that is sitting at that location. So then we do our field solve with our rho J, and then we need to gather back our forces. And to do that with the momentum conserving algorithm, we're going to interpolate using the electric field on the nodes. And we're going to do that interpolation using the same interpolation as in the scatter. Now that's really important because that's what gives us the momentum conserving property of this algorithm. As we've already seen, but I want to revisit, MPIC suffers from, we're going to call this algorithm MPIC for the rest of this presentation, just to distinguish between all the different algorithms that we'll have flying around. So MPIC suffers from this grid heating instability. And as a reminder, we are doing a one-dimensional electrostatic simulation, periodic boundary conditions, electron beam through a neutralizing background density. That's going to follow us through this whole presentation. And now we want to understand how this instability occurs across a wide range of parameters. So what we did was we varied the beam velocity of this electron beam, and we varied the thermal velocity, the thermal spread of those electrons in the beam. For both of these quantities, we normalized by the plasma frequency and the grid cell size. And then we ran simulations at each point. And we measured the maximum growth rate over a short period of time in the thermal velocity. And we declared that that was the grid heating growth rate. And so that allows us to create this nice heat map that shows how the instability occurs in this area. So areas of yellow here are areas with really high grid instability. And that's an area where you'd struggle to run a PIC simulation for many plasma periods. Areas of blue have little to no grid instability. And so you don't have to worry so much about it if you want to run a PIC simulation in that regime. Notice that this scale is logarithmic. So these areas of high instability are really quite unstable. And we can see here that the conventional wisdom is reflected in this plot. For all beam velocities, at a sufficiently small thermal velocity, and thermal velocity is related to temperature, which is related to Debye length. So at a small thermal velocity or a small Debye length, there will be an instability. And so that this is occurring when we aren't resolving the Debye length sufficiently well. So let's say that we are sitting here at this point and we want to run a PIC simulation, but the length of time we want to run for is too long given the instability growth rate at this point. What can we do? Well, the thermal velocity and beam velocity are fixed by the physical problem that we want to simulate. And so is the plasma frequency. We can't change those without just giving up on this problem and basically choosing to simulate another. So the only knob we have to turn here is the grid cell spacing. And that constrains us to lie on this line here that passes through the origin. And so from here, we could choose to, for example, use a cell spacing that's twice as large, but of course that's going to make the Debye length even less resolved and pull us further in here into an even more unstable region. What we are forced to do is use a more fine grid with more grid cells out here, which then puts us in a region where we are able to stably run our simulation. Unfortunately, as we've previously discussed, that is slow. And so we don't really want to do that. What else can we do? Well, you'll notice here that I've labeled this plot MPIC1. That's because we're using area weighting, aka first order B-splines. How about using higher order B-splines? Well, it turns out we can do that in VSim. Here's how. You will have to do a text-based setup. The first thing we need to do in the grid is increase this max int dep half width. That basically tells VSim how wide the stencil, the maximum stencil that we're going to apply, that we're going to interpolate either charge or forces from. And so in a area weighting simulation, this would be 1, but we need to now make it wider so that we can do these higher order interpolations. Then we're going to come down to the multi-field, and we need to delete all these overlap statements in every field. So the nodal E and the nodal B and these ... dots are colored red to remind you that we need to do that for every other field. These overlap statements tell VSim how it should set up the fields on each rank so that MPI processes can communicate back and forth about overlapping edges of the field. But it turns out that VSim's actually smart enough to figure out the appropriate amount to do this if we specify this max int dep half width statement. So we'll just get rid of those. And then we need to tell VSim that we want to use a higher order interpolation. So in the nodal E and nodal B fields, we'll add this ECirc second order to do second order B-splines. And then also in the scalar depositor, we need to tell VSim that we want to scatter using a second order B-spline as well. And that statement here, kind equals ECirc second order. If you're wondering what ECirc is, that's short for Circopov. He did some foundational work in charge conserving current deposition, and now his name has become attached to these B-splines. Unfortunately, using this higher order PIC doesn't totally get rid of the grid instability. So you can see the area weighting or first order PIC up here, and then the second order PIC down here, MPIC. And you can see that there is a reduced need to resolve the Debye length, but it hasn't completely gone away. Darn. So what else could we do? Well, how about an energy conserving algorithm? So in this energy conserving algorithm that we're going to call EPIC for this presentation, we use the same scatter step. However, for the gather, instead of gathering or interpolating electric field values, we interpolate electric potential values. And instead of using the same shape function, we use the derivative of the shape function and the derivative of this with respect to this coordinate xi. Now, it turns out that if we choose to use an interpolation that is an mth order B-spline, then there's this nice relationship between the derivative of an mth order B-spline and the m-1th B-spline. And if we substitute this relationship into our gather step, then we find out that we can equivalently compute the gather as an interpolation of the edge electric fields using a B-spline one order less than our gather step. And this is great because en route to computing the nodal electric field values, VSim actually already computes edge electric fields. And so we can just hook this right into VSim. So to do that, we again need to increase this max int dep half width and delete the overlap statements. The interpolations in the multi-field this time need to be one order less than the overall interpolation order that we intend to use. Unfortunately, VSim doesn't have an ECirc 0th order. I guess they didn't think that anyone would be crazy enough to want to use nearest grid point interpolation, which fair enough. But so we're going to do second order EPIC here. And then you'll notice we don't actually need this nodal E field, at least to advance the simulation anymore. So you could go ahead and get rid of this. But you need to be careful because if you have, for example, history that is computing electric field energy, it's going to be using this nodal E field. And so maybe it's better to just leave it in place if that's happening. It doesn't use that much more processing to actually compute this nodal E field. Then a few more things. We need to, again, update the scatter step. Remember, we're doing second order EPIC, so we need to use ECirc second order here. And then we need to tell VSim that we want to actually interpolate from the edge electric fields, that's called E in VSim, rather than the nodal electric fields. So we need to update this fields statement in the electrodes. Unfortunately, this doesn't totally solve our problem. EPIC still has a grid instability. Energy is conserved. You can see this black line here. However, the instability converts beam energy here in green into thermal energy here in blue. But what does the instability look like in this larger parameter space? Well, it has this interesting shark fin shape. So here is EPIC second order. This is the thing that we can implement in VSim. I also have results for EPIC first order. This does a first order scatter and then a 0th order or nearest grid point gather step. This was run in code that I've written myself. And I want you to notice one important thing about these EPIC 1 and 2 results. And that is that along the y-axis, so at 0 beam velocity, but non-zero thermal velocity, these methods are stable. And that means that if you're simulating a stationary or roughly stationary thermal plasma, then no matter how well you resolve the Debye length, there will not be a grid instability. And so that's really exciting because for a wide class of problems, any sort of stationary thermal plasma, this gives you the ability to run simulations without having to choose your cell sizes based on the Debye length. Instead, you can choose your cell size just to resolve the instability or to resolve the physics that you actually care about. And there's also this interesting region of stability out here for sufficiently large beam velocity. We're not really going to worry about that too much. So now I want to shift gears and ask the question, can we just get rid of the grid entirely? These interpolations cause all these problems. It sure would be nice if we could just come up with a method that didn't have a grid, and so we never had a grid instability. Well, we definitely can't do pairwise interactions between particles because that scales as the number of particles squared, and that's way too expensive to run. The reason we're doing PICS simulations is because we want to run these large simulations. So how about Fourier modes? That's another way that we can run a gridless simulation on a computer. So we're going to follow Astafiev and Chadwick here for a few minutes, and then we'll veer off course from them. To start, we've got to take a look at the Low Lagrangian. So this allows us to derive variational PIC algorithms. And what I've written here is a Low Lagrangian for an electrostatic PIC algorithm. So no B fields running around. And this has three terms. It has a kinetic energy term for the distribution function, so for the electrons. It has a field energy term, and then it has a coupling between the electrons and the electric field. And I'm not going to do this for you, but I promise, and you could work this out on your own, that if you vary this with respect to the distribution function, you'll get the Vlasov equation, the electrostatic Vlasov equation. There won't be a magnetic field. And if you vary with respect to phi, you'll get the Poisson equation. And so this gives us all the tools we need to derive variational PIC algorithms. Now, we want to actually have a PIC algorithm, not some Vlasov type code. So we want to discretize the distribution function as a sum of macroparticles. And so we're going to have these macroparticles that have an infinitesimal extent in both position and in velocity. Then we substitute this distribution function back into the Lagrangian here and a little bit of cranking, and we get this semi-discretized Lagrangian here. So you can see that we have discrete particle quantities now, but we still have a continuous field phi. And now we need to come up with some way to discretize that. So following the intuition we had earlier, what if we eliminate this using Fourier modes? So if we choose to represent phi as a truncated Fourier basis, this truncation makes sense because we're always going to have to cut off the frequency somewhere. Then if we put this phi into this semi-discretized Lagrangian, vary with respect to x, vary with respect to these phi sub k's, and what we find is a scatter step that looks like this. So for each particle, we are computing its contribution to the kth electric field, charge density mode. And then together, for each mode, we're computing its contribution, its electric field contribution to the ith particle. Now, I need to tell you how to do a field solve for this new algorithm, but that's actually easy because Fourier modes are the eigenbases of the Poisson equation. And so we just get to divide each charge density mode by some constant, and we get an electric field mode. Perfect, easy. And this works great. It totally eliminates grid instabilities, regardless of the beam velocity or the thermal velocity. But it does it at an unacceptable computational cost. So for PIC scaling, we want something that decouples the number of particles per cell and the number of either field modes or grid cells, however we've chosen to discretize our field. And this new method does not do that. You can see here that for each mode, we have to talk to each particle, and then for each mode, or for each particle here, we have to talk to each mode. And so this scales as the product of the number of modes and the number of particles. So that is just unacceptable. We can't run these large-scale PIC simulations using this kind of method. And so we need to somehow get back a grid. And this is where these cubic interpolating splines come in. And so the first thing I need to do is pause and apologize for the confusion, because these cubic interpolating splines are completely different from a third order B-spline that I was talking about just a few minutes ago. So where those B-splines are a local interpolation of field values, these cubic interpolating splines interpolate over an entire field, and it's a global interpolation. The way a cubic spline works is, given some values on a field, we can construct the cubic spline interpolation by interpolating the values on the field using this interpolation here, this W sub 1. And then we have this other field, F double prime, that we're going to interpolate using a different weight function, W3. And you can see both of those interpolations down here. One nice thing about these interpolations is they're both over the restricted domain X is less than 1. That means that these cubic interpolating splines have a compact stencil. So they only talk to the grid cells that are surrounding the particle that we're interpolating from. And the other thing I need to tell you is about this F double prime, because it turns out that to get this nice property of cubic interpolating splines, that they're continuous and they have continuous first and second derivatives, we have to do a global solve to calculate what F double prime is. And so that's kind of a drag, because we're already doing a global solve to figure out what to compute our electric field in a standard PICS simulation, but now we're going to have to do 2 global solves. That is not great. Well, it turns out that if we choose to approximate a Fourier mode using a cubic spline, then that's actually not the case. And we can just go ahead and pre-compute what these double prime fields should look like. And we're just going to wrap up all this complexity in a C sub k and leave it bundled in there. The other thing you might be worried about is how well can these cubic splines really approximate Fourier modes? A sinusoid is a pretty special shape. It has all these special properties. And are we really going to come that close by just using a bunch of polynomials? Well, here I have in black a Nyquist mode. So this is the shortest wavelength mode that is resolvable by this grid. So you can see that there are two nodes per wavelength. And I've constructed a cubic interpolating spline shown in dashed red here based on just the field values here. And you can see that they agree really, really well. And this is the worst case scenario, because for modes that have a wave number shorter than or a wavelength longer than the Nyquist mode, the cubic interpolating spline is going to have even more data points to work with. And so it'll be able to have an even more accurate interpolation. So let's try discretizing the electric field using these cubic spline approximations. To do that, we just replace the Fourier modes here with our spline approximations. And we put this into the Lagrangian and we crank, crank, crank. And what we find is that to scatter, the scatter step has 2 different fields. That's kind of expected. We've got a row and a row double prime. And we interpolate both of these fields using this W1, W3. Then together, we're going to gather now from 2 different fields. We've got a phi j here and a phi j double prime here. And you'll see we're using the derivatives of these interpolations, but that's not a big deal. We can work out that analytically. I also need to tell you how to do the field solve. We've chosen to do this in Fourier space. And so we can Fourier transform our rho j and rho j double prime to come up with a rho k. Then we're going to pretend that these cubic approximations are actually the Fourier modes. And we'll pretend that each one exactly approximates the Fourier mode that it's supposed to be. If we make that assumption, and we think that's a good assumption because these are really, really close, to the modes that they're supposed to be, then again, it's really easy to do this field solve because we're working in quote unquote the basis of the Poisson equation, not quite, but almost. And then we need to compute an inverse Fourier transform to come back to the spatial domain. So how well does this work? Well, PICS does have a slightly reduced region of instability. The thing to compare this to is EPIC1 because that has a nice compact stencil as well. But what we're really excited about is that if we choose to apply a binomial smoothing operation to the fields, to the charge density fields here before we Fourier transform it, then we get this really excellent behavior with very, very little instability growth rate. We've also looked at the convergence of PICS in K delta X. To do that, we set up a plasma oscillation and we measure the frequency of that oscillation relative to the plasma frequency. And then we measure how that error changes as we increase or as we decrease the cell size so that we have more cells per wavelength. And what you can see here is that all these other methods, MPIC, all the momentum conserving, and all of the higher order energy conserving algorithms live up here in this second order error, whereas PICS has fourth order error. So it converges towards the correct solution more quickly. And you can see this point here is not really agreeing with what I'm saying. That's because we're actually running into time step issues. And so the time step is now the limiting factor in in our ability to resolve the appropriate plasma frequency. And that's even with running these PICS simulations with a time step that's 5 times smaller than the time step I ran the rest of these simulations with. You might be a little interested in this EPIC1 here. It seems to be doing something a little different. And that's just because EPIC1 is actually, you can actually derive EPIC1 variationally as well. Just an interesting side note. So as I finish up here, I just want to put up a plot of all of the different algorithms so we can compare their instability behavior. You can see this momentum conserving algorithm has this behavior where it is unstable regardless of the beam velocity for small Debye length, whereas all of these energy conserving algorithms have this more shark fin type behavior where they maintain this stability when there's no beam velocity, regardless of the thermal velocity. And you can see that PICS has a slightly reduced instability, region of instability compared to EPIC1, which has a comparable stencil. And it's a little worse than EPIC2. But you can see that applying this binomial smoothing filter really improves things. So what have we done? We've measured the instability growth rates for MPIC and EPIC, and we've shown that EPIC can be used in VSim. And I'd encourage you to play around with this and consider using EPIC when you want to simulate stationary thermal plasmas, and you don't want to have to worry about resolving a Debye length. I've also shown that we have this new PIC algorithm that we're developing, and then it has even more favorable behavior. It has a smaller region of instability with this compact stencil, and it has fourth order convergence in the grid cell size. Thank you. I'll take any questions.
All right, very nice. Luke, thank you so much. So there is a Q&A box on the bottom of the screen that if you click on it, you can type in any questions that you have, and Luke will answer them. So let's see. So what is the difference? I have a question here in computational cost between EPIC and PICS.
Yeah, that's a good question. So in the scatter step here, you can see that we're still just doing an interpolation over the particles onto grid cells, only we're doing it twice. And the same is true for this gather. We're just doing 2 interpolations. And then in the field solve, we're just performing 2 Fourier transforms. and 2 inverse Fourier transforms. So I would expect that the cost is almost exactly twice that of EPIC.
Very cool. And the energy, another question, the energy conserving algorithm EPIC uses nearest grid point interpolation for the scatter step. How does this affect the particle noise in the simulation?
Yeah, so a kind of interesting side effect of the way that I've chosen to measure these growth rates in this kind of ad hoc way is that when there isn't an instability, the measurement is really kind of measuring the kind of maximum short-term fluctuation in the thermal energy. So that's kind of an indirect measure of noise. And so if you look at the background here, you can kind of see, based on if it's a lighter blue or a darker blue, how much noise there is in the simulation. And so you can see that, yeah, EPIC 1 here, that's using a nearest grid point interpolation, definitely has a little bit more particle noise. So that's a trade-off you're making in return for using a larger cell size that allows you to not have to resolve the Debye length.
I see. How many particles per cell did you use? Because it has a strong effect on grid heating as well.
Yeah, I used 60 particles per cell usually in these simulations. But that's a good point, and I'd like to look at the dependence of that.
Okay. Another question we have, how do you obtain those known values for spline interpolation and how to choose those points?
Right, so let me find, right, so the question is basically, how do you choose these? So yeah, this is kind of an interesting point in the derivation, is that we just go in pretending that we know how to find these when we make this substitution with these cubic spline approximated Fourier modes. And then as we do the variation, it turns out that a way to compute them pops out. And the way that it is that you can compute the values here is this scatter step.
Does energy conservation algorithm ensure charge conservation too?
Yes, although charge conservation is not that big of a problem when using these electrostatic methods. Yeah.
Okay.
Right.
Are there any disadvantages to using EPIC all the time?
I mean, so yes, if you have a plasma, let me find, that you're trying to simulate that's sitting, say, here, then like we discussed earlier, the only way you can move on this graph is constrained along this line. And you can see that you have to use a quite fine cell to eventually resolve the plasma. And so if you have plasmas that have a really strong beaming property relative to the thermal velocity, then EPIC is probably not a suitable choice.
Sure. Let's see. Have you, we have a question just about, have you written a document with all of these details? So one of the things that I can say too is, depending on permissions, we are going to try to get presentations available, just like, so all of the talks are going to be, they're all being recorded right now, and the hope is to have all of them done and on YouTube edited next week. And then as far as presentations, I am working to get all of them here. So if there are specific presentations and there's not any kind of permissions issue, that can be something that we can pass out. So, or certainly pieces of it. The answer. So have you, but the question specifically to you is, have you written a document with all these details?
Yeah, so as far as the PICS stuff goes, there's a paper that's being written about that. As far as the EPIC in VSim details goes, I do have a document written up about that. Currently it's on my lab group's server, but I'd be happy to share that with you if you want to get in touch, or maybe we can find a way to publish that somewhere on the TechX website.
Yeah, if you can send that to me. This is from, I know this gentleman, so I can get it over to him.
Okay.
So yeah, send that to me. I think that would be great. So another question, can I, so if you can, if in the Q&A, can I say this, a plane wave expansion as a basis, can that be replaced with cubic spline basis?
Yeah, that's basically what we're doing, is we're replacing this Fourier expansion with an approximation to that using a cubic spline basis. And then we're pretending it's still the Fourier expansion when we do the field solve.
Okay, great questions. Does anyone else, we still have a few more minutes of Luke's time here. If anyone else wants to type something in that they have. Great job, Luke.
Thank you.
You know, doing this webinar for us. So at this point, so I'll just say my kind of final before we wrap up here. So this, for anyone, and you guys are all going to get so tired of me saying the same thing, but if you do not have a copy of the latest versions of our software, you can request one by going to our website, which is txcorp.com, txcorp.com, and you can request, just go ahead and do the free evaluation, even if you own a current license, but you would like to test out the newest version and see, or you want to try out one of our other products like our radiation software, VSim. That's certainly something that we can set up for you. So our next presentation coming up, we've got about 45 minutes until our next talk. That is actually going to be Catherine Wolfinger talking about optical field ionized plasmas for particle acceleration, formation, and terahertz radiation generation. So that will be coming up at 11:30. And it looks like that's good for questions that we have. So thank you so much, Luke. Thanks everyone for watching. We will be back in about 45 minutes.